robot makers, hope you're having a good day so far. So do you want to know why people are making the switch to Micropython and CircuitPython? Then this is the show for you. So let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let's get straight over to a couple of slides, and we'll get into a bit of a demo as well, a bit of a side-by-side coding. So why is everyone switching is the question. So what, of course, is Micropython? If you're not familiar with this, it's a smaller version of the full Python language, and it's designed for use with microcontrollers, hence micro and Python. Python, of course, gets its name from the TV show Monty Python. Apparently, Guido van Rossum, the inventor of Python, the Python language, was a great big Monty Python's Flying Circus fan, so he decided to name it after that. It's a bit of trivia there to get you started. So a quick history of Micropython. So this was created by Damien George not too long ago, just over 11 years ago, and the initial release was on 3rd of May 2014. So it's quite a fresh language, but it's had quite a lot of development in that time, and it's certainly good enough for people to use day to day. So it's actually a program that runs on microcontrollers, and itself is written in the C language. And the logo is a big M, which is kind of like a Python snake. And you can see on screen there, that's the original Pi board that Damien created with an ARM processor on there. So it's available on lots of different microcontrollers nowadays. So it can be installed on any 32-bit microcontroller. So unfortunately, you can't install this on the original Arduino, which I had around my desk. There we go. So this original 8-bit Arduino, you'll not be able to install it on there. But if you have an Arduino Nano ESP32, I've got a couple on the desk that we can have a look at in a minute. It runs very nicely on there. Or of course, if you've got a Raspberry Pi, which I've got just here, Raspberry Pi Pico 2W, Pico 2, it'll work fine on all of those chips. So yes, it's designed to work on most microcontrollers. They need to have that 32-bit capable processor. You'll see a small thumbnail when you go to micropython.org of all the different boards that are supported there. You just click on the one that matches your board, and then you can download the little UF2 file, which you can then flash to the board. If you want to flash MicroPython, I did do a video on this, and there's also instructions on kevsrobots.com. Just search up how to install MicroPython, and you'll find what you're looking for there. So I did a bit of research for this show, and I was looking to see, quite biasedly, are people looking to use Micropython more than Arduino/C++? So this is more about, when I say Arduino, I mean the programming environment that's used, so the C++. When you program a Arduino board using the Arduino IDE, you're actually using a language that's called processing. It's very, 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 very similar to C++ in syntax and everything, but the reason you call them sketches is originally it was designed for artists, and the idea was it would get them away from the kind of complexity of programming, and that's why the language of sketches came about. So when I talk about Arduino, I'm kind of talking about C++. Why are people moving from that to Python and MicroPython? So Raspberry Pi Pico sales, we had 4 million of these sold since they were originally created. Them figures were as of 2024, so I'm sure there's a lot more of those sold now. Of course, there's a lot more Arduino sold worldwide, and they can use C, or they can use MicroPython depending on the type of processor that they use there. All the Picos, they can run MicroPython, of course. The Arduino newsletter, which they have, is the Python on microcontrollers. That's hit over 11,000 subscribers with a higher than average growth rate, so they're really sort of performing well there. You can see on the little chart on the right hand side here, this is the starred repositories on GitHub. So the number of Arduino starred repositories versus the MicroPython starred repository. So people are really going for MicroPython and MicroPython based projects on GitHub. It's a bit of a thumbs down there from somebody. Let me know what you think about that in the comments. So why are people switching? So MicroPython, as I will demonstrate very shortly, makes a really excellent choice if you're beginning, if you're new to programming and you're teaching it, or if you're learning it, makes it very, very easy to do that. And DigiKey have got an article on there. You can follow that link if you wish. has an interactive read, execute, print loop. So this makes it really quick to develop things, to try things out, to change your mind without having to compile the code. The code works immediately, instantly, and that instant feedback is what makes MicroPython quite special. Python is the second most popular language in 2022. I think if you look on most of the boards nowadays, it's the most popular language. It's the language of AI. It's therefore growing in popularity all the time, far more than JavaScript, Java, or C even. So it's the language that people are looking for nowadays. And it's also very beginner friendly. It's beginner friendly, and it kind of gets out of the way as a language. We'll have a look at exactly what I mean by that in a couple of slides. So when to use it. So if you want to use MicroPython when you're prototyping something and you want a fast iteration, you want to be able to develop it quickly, debug it, the REPL is amazing for that. We'll have a look at why that is in a second. If you're building Internet of Things devices, so I've got an example of this is the Arduino Q, for example. This is the kind of device you could develop Internet of Things on. Of course, you could also do that with the Raspberry Pi Pico as well. If you want to process data, handle complex logic, Python is great for that. If you're teaching programming or building electronic educational projects, it's also very good for that as well. Again, it's this simplicity and the cleanness of the language. We'll have a look at that as well. And development speed matters more than peak performance. And this is one of the things I always come back to when people ask me why my Python over C or C++, because C is faster at execution, but most of the time, particularly in robotics, you don't need that level of speed. Development speed matters more, so you're going to read this code more often than you're going to be writing this code, so it helps if the language itself is quite easy to read and is clean, and the speed of actually testing your code out and then making changes is also really quick. If you're comfortable with Python, MicroPython is exactly the same. There's just a small bit of extra stuff that you need to learn around the hardware. So when to stick with C++, that's when you absolutely need that maximum performance of that microcontroller. There's very rare occasions where I think that is actually the case. I'd be interested to know in the comments if you have a use case where you absolutely need that speed of C++. If you're working with time-critical operations to the microsecond, where you need that kind of precision, C++ can help you with that. And if you need the smallest possible memory footprint, C++ is also great at that as well. So with MicroPython, there is an overhead of the interpreter, and objects in memory take up a little bit more space as well because they have things like reference counting and so on. We can have a look at what all that means later on in the demo. If you're using a special Arduino library that's not been ported to MicroPython, that might be another reason to stick with C++. And if you're using some kind of battery-powered device where every milliamp counts, then again, you might find that C++ is a bit lighter on power usage, just because it doesn't have to have all that interpreter in the background. And if you need to integrate with existing C++ code bases as well, that might be another reason to stick with C++. So let's have a bit of a side-by-side code comparison to see just what the differences are there. So there's three main differences I would say between MicroPython and C++ with Arduino. There's no semicolons on the end of your lines, which makes the code, I find, a lot easier to read. It just looks cleaner when you're looking at it. Indentation defines code blocks, so you don't have these curly braces. That annoys some people. For me, it just makes the code look tidy, and you kind of get that automatic tidiness of your code because of the way that you use indentation. You can, with C++, make some really ugly code. You can have everything on a single line if you wished. Why you'd want to do that, I don't know, but Python makes your code more beautiful. And there's no need to declare variable types with Python as well. We'll have a look at what that means in the demos as well. They're the three big changes. So no semicolons at the end. So on the left hand side we've got some MicroPython. On the right hand side we have some Arduino/C++ code. And you can see they're doing the same kind of thing. So the LED pin equals 13. On the right hand side, LED pin equals 13, but with semicolons. And they're just extra bits of cruft at the end of the line that just tell the compiler that this is the end of that particular statement, and what comes next is its own statement. Python just assumes if you've done a new line, then it's a new statement. So it's kind of implicit in that. It can assume that. So again, it just looks cleaner to me. It's easier to read, and it can do some kind of intelligent understanding in the background. We'll get onto that in a few more slides time. So dynamically typed. So C++ is what they call strongly typed. That means every time you declare a variable, you have to say what type of variable it is before you use it, and that's because the compiler can then reserve that amount of memory in its memory space on the embedded device, and therefore it's going to be locked into that. So if you have a byte, it's going to be 256 bits of memory, and it'll allocate that in memory for you. If you've got a string, you probably have to define what that string length will be. It can't dynamically grow necessarily with C++. In Python, all the types are inferred. So if you say count equals 0, 0 is an integer, it's a whole number, so it knows it's an int type. If you say temperature equals 23.5, it's a floating point number because you've got that floating point in there. It knows that that's a float. If you say is running is true, it's a boolean. It knows that it's either true or false. You have that capital T as well in true and a capital F in false. If you say message equals and then speech marks hello, it knows it's a string because you've put it in speech marks. And if you say letter equals A, you can have either double speech marks or single speech marks. That's also a string, it's just a string of a single character. In C, you have to define those types, like I said, up front. So int counter equals 0, float temperature equals 23.5, the boolean bool is running equal true, string message equals hello, and then character letter equals A. So in C, if you say character, it'll just be a single character stored in there. I think it reserves 2 bytes if I'm not mistaken. Depends on the actual architecture, but it can reserve 1 or 2 depending if it's Unicode or not. So it's a lot easier, I think, to write Python code. There is a bit of a danger there because if you can actually change the type of an object midway through your program. So you could say counter equals 0, and then later on you could say counter equals Kevin, and it would be happy with that. That's a completely valid thing to do in Python, but it's quite a dangerous thing to do if you're writing code and the rest of your code expects counter to be an integer. So you can trap that, you can look at that, but the compiler typically won't help you with that unless you use something called type hints. And type hints are pretty much doing what happens on the right hand side there. You can define what type that you intend this variable to be in Python. You can still change it later on, but the compiler can at least see that this intended to be an integer, for example. So that's one of the main differences there. Python is dynamically typed, and just got a typo there I can see as well in the Python, and then C++ is strongly typed, so you set it and then that's what it's going to be, and the compiler can catch bugs with that as well. Now when you come to printing out error messages or debugging your code, Micropython makes this really simple. So you can say, for example, print value, and then it'll print the value to the REPL. If you're using an Arduino IDE, you have to do serial.begin, you have to specify the baud rate of the serial output. You can then define a value, you can print that value out, but you have to separate your print statements from your value statements in that kind of way. And it's just kind of a bit more ugly, I think, and takes a lot more lines of code to achieve the same thing that happens on the left hand side there. It's just a lot simpler. We'll get into those F strings a little bit later on as well. There's something that Python can do that can just help you use less print statements. Okay. So control flow, if statements, logic, and loops. So they pretty much work in the same kinds of way between Python and C++. There's no kind of extra loop controls. What you will notice though is how blocks of code are defined. So in Python we don't have curly braces, we just have indentation. So you can see there we've got the if temperature is greater than 30, we then got that colon, and then we have 4 spaces indented, and then LED dot on with the brackets print hot. So there's 4 spaces of indentation. That tells Python that this is a code block, and then when you stop your indentation and go back, that's the end of that code block. On the right hand side we've got a typical kind of C program, so you're defining the temperature as an integer, and it's 25 to start with, and if the temperature is greater than 30, then we've got these curly braces and we have our block of code in there. That does also happen to be 4 spaces indented, but it doesn't have to be. So you could have them completely left aligned. Your code wouldn't read very well if you're looking at this just visually as a flow on the screen, but but there's no number of spaces that this needs to be in C. It just ignores all white spaces. And the curly braces just tell it it's the end of the code block. So when I'm looking at this code on the left hand side, for me that's a lot quicker to sort of parse mentally. I can just see temperature equals 25. There's no extra cruft, there's no extra bits and pieces there. It's just the variable, the equals, the defining of what it is, and then the value 25. It's really, really simple. On the right hand side you've got int temperature equals 25 semicolon. There's just a bit more going on there, and particularly if you're teaching somebody how to program, it can make quite a bit of difference if it's just simpler. It means there's less for them to learn and less for them to get wrong. If you're typing something out, you forget to put the semicolon in the right place, the code will error on the line above rather than that line. You get all kinds of horrible things happening there. So it's just all easier. You just have to remember about the indentation, and that makes your code look nicer to read anyway. So another important thing there, Python doesn't have plus plus or minus minus. That's where C++ gets its name from, I think. It's one of the conventions that they brought in. And it just means whatever the variable is, add 1 to that. Minus minus means decrease the variable by 1 value. In Python we have plus equals and minus equals. We have times equals, divide equals as well. And that will divide or plus or minus by the extra value that you put on the right hand side there. So it's kind of a nicer, more clearer step of what's going on there. So infinite loops in Arduino, we have the main code runs in the loop. So this is, all your Arduino programs, you'll have a setup and a loop. A loop is kind of like the main program. In Python, we can create this explicitly. You don't actually have to have this. You could just have your script and have a block of code that gets executed. But typically you have like, def main, which is your main program. And then later on you might say, if name doesn't equal main, then run this block of code. But anyway, if you want to have the equivalent of a loop, you just say while true. So a lot of programs in Python and Micropython have while true, and that just means run forever until the power's taken away, and then restart from the beginning when the power's resumed. And you can see there, so while true, LED goes on, time.sleep 1, LED off, time.sleep 1. And on the right hand side, the exact same code, but in Arduino. So void loop. Void, I always think, is a really odd name to have for a function that doesn't return a value. Void. I always think about those scratch cards where it says void if removed, like it's invalid if it's removed. So void, I don't know, it's just an odd word, I always think. And then digital write LED pin high, delay, digital write LED pin low, and then delay. We'll come back to those delays and times a little bit later on as well. So functions work a little bit differently in Python. So instead of declaring types like you do in C++, you just use the def, so define function keyword. So the biggest change, there's no mandatory setup and loop functions in MicroPython. We can just create whatever kind of loops we wish in our program. You don't have to have a setup one. So you can add numbers in this example on the left hand side. So def means create a function for adding two numbers together, a and b. They're the parameters, the arguments, if you like. And then we're indented for, which means that this is the code that's within that function. So return a plus b. It'll just return that value. And then the next function that we have, which is blink LED, doesn't return a value. It just does the blinking of the LED. So pin on and pin off as many times as we pass in there, and for the pin that we pass in as well. On the right hand side, you can see the exact same code in C++. So int, add numbers. So we're going to return an integer. You've explicitly defined that in your code there. And add numbers is a function because it has the brackets, the rounded brackets, is that the right word? Int a, int b, and then return a plus b. So we've got the same kind of language returning. You've just got those extra curly braces, semicolons, and you're actually seeing what time of return type it is. It is actually good programming to tell your reader what type of value you're expecting to return. And in Python, you can actually have different return statements within your code that could return different types, and that's a terrible programming. So you could return like a Boolean, you could return a string or a number, depending on what the conditions are within your function. And that, like I said, is a really bad thing to do, but you can actually do that. So really what we typically will do, we can have a look at that as an example in a minute. You can actually have a return type for your functions if you want to, but it's not, you don't have to have them. So that's one of the main takeaways. You don't have to have functions that have a return type in Python. They just, everything can or doesn't have to. Next up, pin control. So how do we actually control the GPIO pins on our microcontroller? So Arduino has separate functions for pin setup and control. So we have pin mode, digital write, digital read, and we have analog write, analog read as well. In MicroPython, we have something slightly different. We simply use the machine library and then the pin library. We have an ADC function for analog to digital conversion. We have a pulse width modulation, PWM library type as well. So depending on what the function is, we use different classes for that. And again, it just makes our code a little bit easier to read. So you can see there we have from machine import pin, LED pin equals 25, button pin equals 14, then LED equals pin, the LED pin that we've passed in, which is 25, and the pin out means that this is an output pin. And we can also see there we have button equals pin, button pin, pin not in is an input type. So it's kind of defined when we specify what the variable is that's going to be using the different types of pins. On Arduino, we say it's a constant integer, LED pin 13, constant integer, button pin equals 2. And then in our setup, we say pin mode, LED pin is an output, pin mode, button pin is an input. So it's the same kind of thing that's happening, just a bit different syntax. You'll also notice stylistically, when in Python and MicroPython we define a constant value, we always put that in uppercase. And we also use what they call snake case. So we have a little underscore between words. We tend to be a bit more verbose about what our variables do when we define them. Whereas in C++, you have this camel case. We have a lowercase as the first part of the word. So pin mode is two words together. Mode has a capital M, and that's the camel case. Again, stylistically, that's a C++ thing. In Python, we have a snake case, and that's more Pythonic, as they call it. Okay, so next, analog I/O. So analog uses analog read. Arduino uses analog read and analog write functions. MicroPython uses the object-oriented class ADC, analog to digital conversion, for reading analog values, and pulse width modulation for pulse width modulation output. The biggest difference is resolution and duty cycle values. So Arduino uses 0 to 1023 for ADC and 0 to 255 for pulse width modulation. MicroPython boards use different resolutions, typically 12-bit or 16-bit ADC and 16-bit pulse width modulation. So it just means it's a slightly larger number in there. You can see on the example on the left-hand side for MicroPython, on that value equals sensor.read, then it says underscore U16. That means an unsigned 16-bit integer, and that means we get values between 0 and 65,535. That's a 16-bit number. 2 bytes kind of added together there. And then you can see we've also got the sensor equals ADC pin 26, so we can create an ADC object, an analog to digital conversion object, so it'll read in that analog waveform and give us a number value when we do read 16 on there, read U16. On the Arduino side, we can see we've got the void loop. We have the int sensor value equals analog read sensor pin, which we defined up in the setup function a bit earlier up. And then we do, we can print out that value. So they do the same kind of things, we just get a different range of values in there. So typically with the analog read, you get a value between 0 and 1023. So just another little difference there. Timing. So the most important difference, there's a single biggest gotcha when moving from Arduino to MicroPython. Arduino uses milliseconds, MicroPython uses seconds for the delay and the sleep functions. So this one difference causes more bugs than anything else, and then make sure you fall for that. So on the left hand side in our MicroPython, we have time.sleep1, so that means sleep for 1 second, or sleep for 0.5, sleep for half a second. On the right hand side in Arduino, we have delay 1000, and that means wait for 1000 milliseconds, which is a second, or wait for 500 milliseconds, which is half a second. So if you put that into your code, you'll be waiting, is it 18 minutes? It's quite a long time if you wait 1000 seconds. And for precise timing, we use microseconds. So on the left-hand side, MicroPython has has this time library that we can use whenever we want to do anything with timing. So time.ticks_us gets us microseconds. So elapsed time, we can use the ticks diff, because the way that numbers are stored in variables, if you have a number and you're counting time, the processor, a bit like a car's mileometer, it'll, when it gets to like 999, it'll all roll back over to 0. So if you're comparing two numbers and you say that number minus that number and it's gone round the clock, you'll get the wrong number. So using ticks diff will always make sure that you get the right difference in time, of time elapsed. And typically microcontrollers just start counting the number of microseconds or seconds that have elapsed since the chip booted up. So they both work in the same way there. On the right hand side, we've got the unsigned long. Start micros equals micros, and that's how many microseconds have elapsed since the board booted. And elapsed time equals micros minus start micros, so we get that elapsed time. Again, you might fall foul for the rolling over comparison. Okay, serial basics. So Arduino requires you to initialize the serial communication with serial.begin. Micropython's built-in print function just works. There's no setup required. So we always have this read, evaluate print loop, the REPL, and that gives you interactive Python console. You can actually start typing code in the second that the board boots up. So you can import time, while true, print temperature, and then if you've got some kind of temperature value, it'll print that out to the terminal, and then we've got a time sleep, so it doesn't just scroll off infinitely. It waits a second between each value. On the right hand side, we're doing the same kind of thing there, but in the void setup we have to say serial begin, the number of the baud rate, so how fast are we communicating over that serial, and then in our void loop we do serial.print temperature, serial.println temperature, and that will print out the word temperature and then the temperature value, and then we delay for 1,000 milliseconds, which is a second. Again, I find the left-hand side a bit easier to read. It's just cleaner. There's less cruft there. These F strings, if you're not familiar with them, these can look a little bit complicated at first, but once you get used to them, they're really, really easy to use. So F just means you can use variables within your strings. You don't have to have a comma and tell the compiler that what comes next is a different thing than the string. You can just have them within the string because they're in these little curly braces, and it will just swap out that with the actual value of that variable. So just a lot nicer. Cool, so that's how we do serial basics. F-strings, I told you we would look at these a little bit later on. So if we've got three variables like x, y, and z, they're equal to 10, 20, and 30, we can then say f-string, value of x, colon, and then in curly braces, the actual variable x, so that'll be 10, 20, 30. We can have a different method by having x colon and then closing the brackets, having a comma, then having the actual value, the variable that's got the value, comma, and then comma space y colon speech marks comma and then the variable again. Or you can do the very old style where you say x brackets, y brackets, z brackets, and then dot format x, y, z, and it will swap out for each of those in order. But if you've got many variables, it can get quite confusing about which one that is. I find f-strings are just so much nicer. There's a new thing in Python that's called t-strings as well, where you can swap out using a template very similar to this. But once it's rendered the output, you can actually query that to see what was in each of those values. You can kind of get them out of the string as well as just putting them in there. So on the right hand side, this is the way you would do this in C++. So defining the variables integer x10, y20, z30, serial print line x, and then on a new line print x, and then on a new line print y. So you've got a lot of print statements. Again, it's just a bit more code. This looks a bit more elegant. We've got three different ways of doing the same thing. So that one line there does what those 7 lines do on the right hand side in C++. So it's a lot more efficient to write in Python. If you like what I do and you want me to make more videos like this, or if you want me to make more hardware videos like Jeff said in the comments at the very beginning, then let me know in the comments what kind of video you prefer, and I will make more of them, because at the end of the day, this is why I make these videos, so that you have something to watch that you enjoy. So definitely like the video if you've been watching this already, and if you have not subscribed, please subscribe. It means so much to me when people subscribe to the channel. It costs you absolutely nothing, and it really helps me out and grows the channel. And we do go live every single, we go live every single Sunday at 7 o'clock GMT. So if you want to follow and chat in the chat before, during, or after the show, then you can do that live. It is a live stream. Okay, let's get into some demos. Arduino versus Micropython. So I'm just going to go over to me for a second while I get my screen up. And I've got two different environments. Let me just move that over there. And let's get over to... I think I might just have to change that to be primary display. Nope, secondary display. There we go. Right, so on the left hand side of my screen, I've got the Arduino lab for MicroPython. So this is just a MicroPython environment, and on the right hand side, I have the Arduino IDE that you might be familiar with if you've written any code ever. So what I'm going to do is write the same code for both programs. They both do the exact same thing, but you can see some kind of differences that we have there. So before I get into this code, I want to just show you that we do have this as a course that's completely free and available to you on kevsrobots.com. Let me just load up a quick browser and I will show you that. So I'm just going to close that and bring this down here. Bring that down there. And let me go over to here. So I'm on kevsrobots.com, and if you go to the free courses, there's this new Arduino to MicroPython course, and it says about 3 hours to complete this. There's a lot of detail in here. We kind of go over a lot more detail than we'll be able to have time in this live stream today, but the example programs and so on, they're all in here as well. So pretty much everything we've covered off so far is in there, but again, a lot more detail. So if you want to follow along, you want to read this in kind of slow time, go to kevsrobots.com for that. Right. So let me just jump back over to what's gone on there. Let me just quit the Chrome, and let's go back over to here. Right. So the first program that we're going to do is we're going to do the Blink, which is one of the first programs I think anybody creates on an Arduino or probably MicroPython. So we're just going to blink an LED. So these Arduino Nano ESP32s, they have a built-in LED on the board. Let me just open this up. I should open this before the show, really, shouldn't it? There you go. Got a bunch of these. I've got more projects in mind to use these. Okay. So what the ones that have they've not got the header pins soldered in, so they're just like a little flat board. But yes, this has got a built-in LED. So at the very top, left and right of the board, there is like a power lighter and an LED built-in light. They also have an RGB LED as well, so you can have all different kind of colours, so these are quite neat. And if I go to the overhead camera, I've got two of these side by side. I've got a Raspberry Pi Pico there as well, but I thought I'd do it on both of these boards. So yeah, this is the one that we're going to be looking at with MicroPython, and this is one that's got C++ programs on, but they're exact same ESP32. So let's get into the differences. So on the right hand side, this is our Arduino C++ code. So the first thing we do is say constant init LED pin 48. So pin 48 is on the ESP32, the Arduino Nano ESP32. That's the pin number for the built-in LED. So if you want to flash that, it's on pin 48. In our void setup, we want to initialize that LED as an output. So we say pin mode LED pin, which we define as 48, is an output. And then we do digital, so we do void loop, and then curly braces, digital write LED pin high. So that turns the LED on. We then delay for 1 second, so 1000 milliseconds. We then do another digital write LED pin and then low to turn it off. And then we have another delay. And because this is in a loop, it'll keep doing this forever. On the left hand side, this is our MicroPython example. So it's pretty much the same size of program. You can see there's just a little bit less code. In fact, we can actually get rid of that one. I was using a different board when I was playing around. I was using these baguette boards. I like the fact that these are called baguettes. Apparently they were looking for a breadboard, a breadstick, we're going to call this, but breadstick had been already taken as a name, so instead of breadstick they went for baguette. I just think that's a really awesome story. So yeah, these are from the Pi Hut. These are basically just an ESP 32C3, I think is the processor. Anyway, let's back to the MicroPython. So we've got some comments up here, MicroPython blinking LED example, and then from machine, so this is how we import the pin library, and then from time import sleep, that's the sleep function, and then we say LED equals pin from our pin library 48 and comma pin out is a pin output. And then while true, this is a bit like our void loop, LED on, sleep 1, LED off, sleep 1. And that does the exact same thing. So if I run this code, it runs immediately. So if I go to our overhead camera, let's kind of do this at the same time. You can see here, oh, it's on this one. This is our MicroPython code. It's flashing that, and we can change that immediately. So if we wanted that to blink every half second, I can come to this code and just change that to 0.5, change that one to 0.5. And if I press the run button, immediately it will change that, and it's now flashing twice as quick. We could have that speed again. We can do so 4 times a second. Let's run that, and if we wanted that to be like really quick, we could say, I don't know, like 1/10 of a second. Let's try that. So you can see how quickly we can change the code, and we can run it instantaneously. There's no compiling, we just change the code, hit run, and we're working right away. So for me, this is one of the key reasons why I think MicroPython is just the go-to language when you're prototyping or developing anything. It just works, and it works really quick. So that development time is immediate. So what I'm going to try now is I'm going to try to get this to work. I did have a few error messages when I tried this last time. So if I just go back to here, I'm going to compile the code on here first of all. So it says compiling sketch, and I'll see my CPU usage rise as it compiles all the associated libraries and makes this into an executable piece of code for that particular architecture. You can see it takes a bit of time to do that. So we could actually time that and see how long it takes to compile. Let me get a stopwatch up, because we need to change our code to see how quickly we can change this. So if I wanted to upload that, I would just hit that upload button, but I think when I tried this last time, it complained about that. Even though I got both boards plugged into a little USB hub, it was complaining about that. So interestingly, you hit upload and it compiles again. Why? We've already compiled the code. Can they not have like a it's already compiled, just upload the hex file to the board? But no, they do a fresh compile every single time. So I think it'll error out there. So yeah, it just says exit status 45. It couldn't find the board even though it's connected to the board, and the board is of an Arduino ESP type. So I'm not sure what's going on there. It's really just how it copies the code up to the board. So if we want to change that value, instead of it being 1000, let's change it to 500, for example, like we did in the MicroPython example. And then we compile it again. I'm going to hit the got my phone up here. Let's hit the start button when I press the compile button there, so we can see how long this will take to actually compile. So on the MicroPython side, it was instant. We just changed it and we ran the code and it worked right away. So I could have changed this value probably 4 or 5 times in the time it takes to compile the C code. Now, albeit the code will run faster on the board, but for this example it makes no difference. The speed that it executes the code on the C++ makes no actual difference. So I'm just going to make sure we can stop that when it's finished compiling. There we go. So that took 37 seconds for it to compile that code. So That's quite a lot. These things add up. So if you say, right, well, we want to change that now to 4 times a second, and we compile it again, it's another 40 seconds. Over here, I could have changed this value like several times. So if I go over here and change that to, 100th of a second, let's try that. Let's run that, see what happens, see how fast our LED starts to flicker now. You can't perceive how fast that's flashing. So let's change that back to a 10th of a second. That seemed to be okay. Meanwhile, our other code is still compiling, and we've made some other changes. So you can see in that very simple example, the speed of development is so much quicker on Python, and it's so much easier to write Python. There's just less code to actually be written in the terminal, and you've got this this REPL. If we go back over to the left hand side here, we've got this kind of interactive code. If I say stop, I can actually start typing in code here, like A equals 1. If I press A, it'll tell me the value of 1. If I say B equals 2, C equals A plus B, and I do C, we can see the value is 3. So you are actually writing code, and essentially all that this code we've written here does is the REPL just executes one line at a time, and it'll keep all these things in memory. If we do LED, for example, does it have that? Yeah, pin 48 that we defined. So it's got all the things up in memory that we defined. One of the differences in MicroPython is just the libraries, the number of libraries that are available. That's growing, but it's probably nowhere near as extensive as the libraries are available for C++. So you've got this library manager for Arduino. So if you wanted to do, I don't know, serial, no, let's go for a servo. So we look on there, there's a servo library there. You just click on the install, and that will download that code to your IDE, and all the headers and all the libraries and the object code will be ready for compiling into your code. On MicroPython, we do have something similar. We have this add packages thing. If we click on that, it will load up this MicroPython package installer. You can see both of the boards are available there, and we can do the same kind of thing. If we look for like servo, there's a Pico servo class that somebody's got, and you can click on install, and that will upload that code to your MicroPython device right away. The other thing that's worth noting on MicroPython is it treats the device as like a file system, so you can actually see the files that are on the board. So if I go back to and connect back up to that one there, you can see we've got this boot.py. If I double click in that, we can see that there's some things have been commented out, but we can essentially run some code in there. We can create, we can upload our Blink example to the board, and we just save the file, the py file as like main.py, and it'll automatically load whenever the device boots up. That does mean that if somebody gets hold of your device, they can read your code. So if you had passwords in there, for example, they will be able to read them passwords. So it is a little bit insecure in that way. But people can do the same thing if they have access to your C++, your executable code. They can just reverse engineer it as well. So it's not one's better than another. They're just different in that way. So that was the first piece of code. So let me go back to the editor. I've got a few different ones up here. So next up we have a servo. We want to do like a servo example. So I've got on the right hand side, if I minimize this one, I think I have a servo one. Let me just find that on my screen. So servo, there we go. Let's just compare these side by side. I can minimize that REPL as well if I want on this. This is the Arduino Lab. You can use Thonny or Visual Studio Code. It's kind of the same thing. So over here on MicroPython, so from machine import pin and pulse width modulation. That's the library we're going to use to define PWM. Import time. And then we're going to initialize PWM on GPIO 13, whatever pin you connected your servo to. So servo equals PWM pin 13. And we can even set the frequency if we wish to whatever we want that to be. So 50 Hertz will be frequency 50. So depending if you're using servos or LEDs, you might use a different value for that, for example. And then on here we've got like set the angle. So convert the angle 0 to 180 to a duty cycle for the servo. So typically we have 1 to 2 millisecond, microsecond pulse widths. and the duty will be 4215 on the ESP32. So duty int, so we're casting the value of the output of this little calculation into an integer. So this might return the code within it a floating point, and casting it into an integer kind of does that little conversion. We do the same thing in C++ as well over there. So 40 plus the angle divided by 180 times by 75, that'll give us the duty cycle, and then we can say servo duty, and that will set the servo to that particular angle. We could encapsulate this in a class, but a function will work just as well. So we can then say while true, so in a loop, for position in range 0 to 181 in increments of one step at a time, and then we say set angle to pos, which is this little variable here, and it'll basically just sweep the servo around to 180. It'll then, in between each setting, it'll sleep for 15 microseconds, and then we have, sorry, milliseconds ms, US for microseconds, and then sweeping back from 180 to 0, we can say range 180 minus 1 in minus 1 step, so it kind of goes backwards. So set the angle position and then time sleep 15 milliseconds again. Same thing on the C++ side, so we include the servo library, servo.h. That's a pretty standard one that comes with Arduino. We then say servo is myservo, so myservo is the name of the variable, servo is the type of class we're using. It's a bit like what we've done over here. They just kind of reverse the orders in C++ to MicroPython. We then got a constant, which is the servo pin. We just have that in uppercase if we wanted to define the servo pin. So we could do the same thing over here in MicroPython by just saying, like, you know, servo pin equals 13, and then instead of having 13 there, you could just have servo pin like so. So that does the same kind of thing there. Again, constants tend to be in uppercase. And then in our setup function, we have myservo.attach. So this attaches the servo to pin 9 using that variable, that constant. In our void loop, we then say for integer position 0, position is less than or equal to 180. So that's the kind of condition that we want our for loop to do. And then we want to increment the position 1 each time. So pos plus plus means that each time it goes around the loop, pos gets incremented. So it starts at 0. It checks if it's less than or equal to 180, otherwise it'll increment it. So my servo.write position will set the servo to that particular angle. So that servo function is doing what that set angle is doing there. We could have this in a separate library if we wanted, and just import that as servo, for example, and it would just make our code look a bit cleaner. But we're doing everything in there. Again, there's a bit of a difference between Arduino and C++, MicroPython and Arduino. So that piece of code will make it swing in a positive direction, and then the other piece of code does the opposite. So pos is greater or equal to 0, pos minus minus. So Dale says, look at so 180. So this is an interesting thing with for loops in using the range. If you say range 0 to 180, it'll never actually get to 180. It'll do 179, and then it'll stop. So you need one value greater than the number that you're after. It's just a bit of a quirk. And then it doesn't do it in the opposite direction. You just have to overshoot, so -1 instead of 0. So just a bit of a quirk in how MicroPython works. Give that a try and see what you find. It's just one of those weird things. So that's how we do servos. If we want to do motors, let's do our motor example. Jump over to motor. These again pretty similar. So this time we're using the pulse width modulation again. So in this example, I'm using something like show you on this robot that I've got here. I've got these little driver boards, and they have 2 outputs like A and B, and 2 sets of input pins, 1 and 2, for example. And this is what you'll find on when you're using these kind of libraries. So motor in 1, that's the like motor A, if you like. You typically have pairs of pins, so you have like a positive and minus pin, and you can actually control them individually. So in 1, pin 25 is pin out, in 2 is pin 26 is a pin out, and we have an enable pin on this particular example, which is a pulse width modulation for defining the speed of the motor, and that's pin 27. And then the frequency of the pulse width modulation is 1000 in this example, so that's what we would do in the equivalent of our void setup, but we don't need to define a void setup. MicroPython and Python run code sequentially top to bottom, so whatever order the lines of code are in, that's the order they get executed in. You have to remember that when you're actually defining functions, because if you try and call a function and you've not defined it, physically above the code that's calling it, it'll say that it doesn't understand that. So then we define the function for motor forward. We define the speed that we want to have that in. Speed is a value between 0 and 1023. And then we say motor in 1 is on, motor in 2 is off. So if this is like this type of robot where there is a motor there and a motor there and a motor there, you can just about see them. We want them to spin in opposite directions to make the motors spin. Make the robot go forward, for example. It's just because they're kind of diametrically opposite. That's the right word. And then we have the motor enable duty. So for reverse, we do the opposite. So when it was on, it's off. When it was off, it's on. Have the speed again. And if we want to stop the motors, we just say motor enable duty is 0. So stop the motors from spinning. And then we have a while true loop. And that will make the motor go forward. So motor forward 1023 full speed, wait for 2 seconds, and then stop, motor stop, time sleep 1, and then reverse at half speed, motor 512, sleep for 2 seconds, motor stop, motor sleep for a second. So on the Arduino example of that exact same code, you can see it looks pretty similar. So constant int motor IN1 is 8. So did we define them? We didn't actually define the pin numbers in the left-hand side. But yeah, same kind of thing. So we're defining 3 constants for motor IN1, motor IN2, and the enable pin. In our void setup, we then set the pin numbers. So the pin mode, motor in1 is an output, motor in2 is an output, and enable is also an output. And then in our void loop, digital write. So we have that special wording there, special keyword digital write, motor in1 high. And this is where there is the big difference between MicroPython and Arduino code. In MicroPython, we can just choose whatever we wish to call that. So on and off, you could have a different function if you liked for that. So in this example here, we're using a pin. So a pin can either be on or off. You can set the value to 1 or 0, and it does the exact same thing. In Arduino, we have digital write and analog write. So these are different special keywords for essentially doing the same thing. So motor enable in 1 high, motor in 2 is low. That makes it go forwards. And we haven't defined in this example functions for going forwards, reverse, and stop. We could do that same thing in the left-hand side and the right-hand side if we wanted to as well. So again, you can see there's all this extra cruft. We've got these little curly braces that we have to remember. So there's in that loop there, we've got one at the very beginning, one at the very end. At the end of each line, we need to have the semicolon. But it's entirely acceptable to have your code like this. Oops, not quite like that. Like this. That could be on the same line as the one above. That will work. That's completely valid. If I do verify, it'll compile that code, but it looks dreadful, and it's not very easy to see when you're reading through that code. Whereas in the MicroPython, if you start indenting code, it won't work. It'll complain that there's an error. If we go over here, for example, put an extra space in front of that, that's not valid. Why would we have that as a separate code block? So if I try and run that, it'll basically just say unexpected indent on line 22, which is what we've done there. So we'd have to go back and fix that, and then it'll work again. Cool. So that's how we would do motor control. I think I've got a couple of other examples on here. So if we wanted to connect to Wi-Fi, let's have a look. We would do that on both. So on the left-hand side, we need to have a Wi-Fi SSID, like your hotspot name and a password for that. So that's where you'd put them, just into some constants. And then to initialize the network station, we would need to import network first of all. That's the network connectivity library. And on here, so we're saying VLAN, which is the variable, network.VLAN, network.staif, that's the station interface, and then WLAN active, that means bring up the network connection, and then we can print out connecting to SSID, whatever we put in that variable at the top, and then WLAN.connect, the SSID and the password, so that's how we connect to our network. And then there'll be an amount of time where it just negotiates and tries to connect, get an IP address and all that. So while not WLAN is connected, we can just print some dots out on the screen and then sleep for half a second, and you'll just see the dots appear on the screen at half a second. Once it has connected, it'll then say Wi-Fi connected, IP addresses, WLAN if config, that's the interface config, and like the parameter number 0 is the IP address. Then netmask, that's like the 255.255, whatever, that's the first parameter after that. Gateway, which is where it routes things through, that's your router. And then the DNS is the sort of name serve that it looks for to convert IP addresses to nice friendly domain names. And then we can have a little loop there. While true, WLAN is connected, Wi-Fi is connected. If we disconnect from that or turn our router off, you'll see it say Wi-Fi disconnected. And we can basically just have a loop where it'll try and reconnect if it gets disconnected. If I try and run that, it'll actually stop because I've not provided a Wi-Fi SSID or password in there. Now on the right hand side in Arduino, a bit more involved on here, so we have to include the Wi-Fi.h. This is the header file for Wi-Fi connectivity. Again, we pass in a Wi-Fi SID and password, but we do have to define these as a constant. Now this char star, I don't know why they've not used a string for that, but that's just what they've gone with for this particular code. So that means a character that might have multiple, there might be multiple characters in the string, so it's kind of dynamic. That's kind of what that means there. So then void setup, serial.begin, we need to tell you what the speed of the serial connection is going to be for the serial port to output stuff to the terminal. Print serial line, so it's going to do a new line, and then print connecting to, and then the SSID. Notice how we have print line and print without a new line at the end. Again, that's just a quirk of how we use that serial print function. And then Wi-Fi.begin, so here's the SSID and password. That's a bit like how we pass in the connect on there. Once we've done that, we can say while Wi-Fi status is not connected, so that bang exclamation mark or exclamation mark equals WL connected. So you have to know those codes to begin with, whereas I think on the Micropython side it's just a bit more elegant. So WLAN is connected. Is connected is almost English, isn't it? Whereas Wi-Fi status exclamation mark equals, so not equal to. We just have the word not in the Python. Again, it just reads more easy. And if you're trying to explain this to a group of, I don't know, 7 or 8 year olds, it's a lot easier to explain while not WLAN is connected. It almost reads like English, whereas while Wi-Fi.status exclamation equals WL underscore connected, it's just a bit more esoteric, I find. So then we delay for 500 milliseconds. We then print a dot, and it'll do that until it's connected. So then we can say print line Wi-Fi connected, print IP address, and then on the print line Wi-Fi.local IP. And then we have, sorry, somebody just said volume too low. Let me just move that a bit closer to my face there. That might be a bit better. Let me know, Paul, if that's any better. And then we have, if you want the signal strength, that's the RSSI. You can grab that from Wi-Fi.RSSI, and it'll print out the how many decibels of volume that is. I think that is. And then we have the main loop. So if Wi-Fi status, let me just move this a bit out of my face there so we can see. If Wi-Fi.status equals WL connected, then we can say it is connected, otherwise Wi-Fi disconnected. And then delay for 5 seconds, I think that is. So this is where I think MicroPython again just shines. It's a bit easier to understand. and there's a lot like less going on there. The only thing that's probably is a bit esoteric is getting the order of the parameters correct from WLAN if config. You could just print out WLAN if config and you'll see everything on one line. I think they do have a signal strength one as well that you can grab. That might be like 4 or 5 in there. And then finally, let's have a look at MQTT. So if we want to connect to an MQTT server, so we need to have the Wi-Fi code that we've just looked at, and we also need to have an MQTT broker, an MQTT port, the client ID, the topic that we want to publish to, and the topic we want to subscribe to. So there's some interesting things I want to show you on this left-hand side here. So we're bringing in this Micropython simple library. You do have to install that as an additional package. If we go to that add package, we can find, if I type in MQTT simple is a very common library that's used for that. There's a more robust version as well, but the simple is probably the most common one used by people. So definitely check that out and upload that to your code if you want to try this example on the left hand side. So we're bringing in network again, we're bringing in machine pin, we're putting our Wi-Fi credentials in there, and then we're setting up what the MQTT broker is. So that's either an IP address or a name. It could be like Arduino Cloud or Adafruit IoT. The port is usually 1883 from MQTT unless you've specified a different one. The client is just so that the server knows who you are when you connect in. It can log that out. And then here, this is an interesting one. So B means that we want these to be bytes in a string. So it'll sort of, when it encodes them as bytes. And it's just the way that MQTT needs to receive these. I think if you don't have them, it can cause problems. So it's just the way that it encodes these in there. So the B just means encode this string as bytes. Then we have the function for connecting to Wi-Fi. We've looked at that one in the previous code, so that's fine. We can create a callback function. So whenever we receive a message from our MQTT server that we're subscribed to, we want to know what topic that's on and what message we're receiving. So we have 2 parameters for that. So we print receive message on topic.decode, message decode, and then in our main loop we connect to the Wi-Fi, we set up our client, which is just a variable of MQTT client. That's from that MQTT simple library. So the client ID that we've called it, the server and the port, and then we set the callback. So whenever a message is received, it's going to run that MQTT function, that callback function that we defined there. We then client.connect, that'll connect to the broker, and we can say client.subscribe to the topic that we want to subscribe to, and then print out subscribe to topic sub.decode. This decode is part of that byte encoding that we looked at the very top, where we've got that B. So it's just an extra step to decode that into a nice string that we can look at. You can try it without that decode and see what happens. Counter equals 0, so we're just going to count how many messages we get there. So client check message, counter plus equals 1, so that's a bit like plus plus in C++. So it increments the counter by 1. And then message hello from MicroPython, and then the counter will be replaced there. So this is like an old school way of doing strings. And then client publish, topic publish, message encode, and then print the message that the messages come through. We put this in a try except block as well, so this down here will run that main loop. If there's any problems, if it gets disconnected midway through, it basically just print out that there's been an error. So exception as E, that's how we handle errors in Python. Or if we press Control-C, it'll just disconnect from there. So that's how we would do that in MicroPython. So quickly then, on the right hand side, this is how we do the exact same thing in Arduino C++. So we bring in the Wi-Fi library, we bring in the pub sub client, and then we define what our Wi-Fi and password is. We define the broker settings, just like we've done on the left hand side there. So that is going to be ESP test data, for example. And then we say Wi-Fi client, ESP client, to get our Wi-Fi client, and then pub sub client, client, ESP client. Which is just that variable that we created from above, I think. So no, sorry, we're passing in to the client, the Wi-Fi connection there. We then got the last message counter, and then we're defining our callback just like we did over here in two lines of code. We've got serial print message received on topic, the message, and then for int I equals 0, I is less than length, I plus plus, it's going to grab each character from that payload and print it out. So that's a bit ugh, but that's just how they've decided to do that. And then reconnect, this code's got an example where it can actually reconnect. So while not client connected, so that exclamation mark before client connected means not client connected, so that'll return like a boolean value, true or false. So if it's if connected is false, that statement is true. So connecting to MQTT, if client connect, zero print connected, subscribe to the topic, otherwise failed, RC equals, and then client state, like reconnect, whatever, and then retry in 5 seconds, and then delay for 5 seconds. And then in our setup we've got serial begin, Wi-Fi status not equal to W connected, delay, print the dots out. Finally we're connected to our Wi-Fi. We can then at that point set up the MQTT, so client.setServer MQTT port, set the callback to the function we defined, and then we get into the main loop. If not connected, reconnect, and then client.loop. So client.loop is just that particular implementation of MQTT. And then unsigned long now millis, so that's going to grab the current time in milliseconds. If now minus last message is greater than 5, last message equals now, counter plus plus just increments it, and then the string message just says that if I just move that out of the way of my face, you can see there we're just setting a message and sending that message, we're publishing that message to that topic. So you can see there that would send a message to the broker. So I hope that gives you a little flavour of some of the differences between the two. But for me, the biggest difference is if I want to troubleshoot this code, I can run this code immediately. Just click on connect to the Micropython device. I can run my code. I've not got my Wi-Fi connected there, so it's not going to connect because I've not typed my details in there. I can press Control-C to exit out of there. But I don't need to compile the code. If I want to go over here and compile this code, let's see how long this one takes to do. Probably going to take longer than 40 seconds. We can give that a bit of a start. I think there's 5 seconds ahead. But we can see how long that takes to compile. It's not going to be 40 seconds. It's probably going to be a bit longer than that. What I will do though is I will jump to the next thing because I don't want to just waste your time talking through that. So I think I've pretty much covered off everything there. I've not really given you like a working example with actual hardware. I thought it'd just be easier to just go through the code today, just to give you an example of that. But yeah, we could look at you know, an IoT project like a temperature sensor. I've got a little temperature sensor at the very back of the studio, which is an ESP32 running MicroPython with a little DHT 2022 sensor on it for detecting temperature. You can see we're still compiling, nearly a minute in. So yeah, that's taking quite a while to compile that code. We could have written quite a few programs on the left hand side in MicroPython for the amount of time we have to wait for this. And I'm compiling this on a Mac M1 on Apple Silicon. There we go, it's just finished compiling. That was a 1 minute 7, probably 1 minute 10 or 15 because I only hit start 5 seconds after we'd started compiling. So yeah, a minute to compile a piece of code that we can run instantly on the left hand side in MicroPython. For me, that's the killer reason that you would want to use MicroPython. It's just so quick to develop in and so easy to read and teach. And read years later when you're looking back at your code. So if you want to join our Discord community, we have got really great community of people on Discord sharing projects. If you want to ask questions, it's easy to share code and screenshots of things that you want to troubleshoot. So head over to kevsrobots.com/discord to check that out. And it's completely free to join. Just pop in your email address and you'll get a link. And I'm on all these social medias, so look at Threads. I'm on Kev McAleer at threads.net. I'm on TikTok, Kev McAleer6. I'll do all the dancing. Maybe not. I'm on Instagram at Kev McAleer. I'm on X at KevsMac. On Mastodon at kevsmac at mastodon.social, and I'm also on Blue Sky at kevsmac.bsky.social as well. So if you're on any of those platforms, give me a follow, say hi, maybe share a picture of a project you're working on. I'm always interested to see what people are building behind the scenes. So if you want your name in the end credits, you can go to kevrobots.com/coffee and buy a coffee as just a one-off thing. If you enjoyed today's show, you want to know more about that. If there's something specific that you want to look at, just grabbing that Arduino Uno Q. If you want me to do more content on this, for example, let me know in the comments and I will do more content specifically around the Arduino Uno Q. So you can buy a coffee and get your name in the end credits is kind of what that page is about there. kevsrobots.com/coffee for details on how to do that. And let's give a shout out to people who have done exactly that. So on the left hand side, my good friend Simon Hodgkinson bought me a coffee. Thank you for that, Simon. Really do appreciate that. Peter H bought 3 coffees. Martin bought 2 coffees. Rory, Jersey IT guy, bought me 3 coffees. Cubeless Corny bought me 3 coffees. And Maria Louise Mayer bought me 3 coffees. That's a lot of coffee. I was quite hyped up when I drank all that coffee, I can tell you. Member-wise, we've got Pietro, got Michael, Warren, Anonymous, Silicon Fiber, Marie TKD, Jeff, Dean Corty, Marlene, and Tom. On the YouTube side, we've got Brian, Grandpa Gray, we've got Shrish Riva. I always chew on your name, and apologies for that. We've got Marie, Pete, Dale from Hybrid Robotics, we've got Orctrad39, Warren, Pierre Eves, Bert, Michael J, Steve, Ford, Bello, Stephen, John Paul, Cassie, Johnny Bates, and of course we have Tom. Cassie, how's your arm doing? I know you injured your arm a while back roller skating. Hope that's on the mend now. So thank you so much everybody for subscribing to the channel and for supporting it. It means so much to me that you've done that. Thank you again. It means I can buy all these new toys such as this Arduino. Where's it gone? The new thing I bought recently. I bought the Arduino Nano 33 IoT, which is a little board very similar to the Nano. It's got Bluetooth and Wi-Fi connectivity on there, but slightly it can't run MicroPython, which is a bit annoying. I also bought this board here, which is this Arduino Nano motor carrier. So it's got all these nice chunky connectors there for motors, and it's also got these nice pins for servos. You can alternatively connect the motors up with these pins here, and you drop your Arduino Nano 33 IoT into that board. You can also plug in the any of the Nano boards apparently, but you can't program them necessarily with this board. This board only supports the R4 Nano or the Nano 33, which is very unusual. But you might be able to see in the very middle of that little chip just there, that's the voltage regulator. There's like a little bump. This board released magic smoke when I plugged in a battery to that yellow connector there. So this board is now toast, and this was about €80 to buy. These are not cheap, so I'm really disappointed with that. I'll get in touch with, I think it was the Pi Hut I bought that from. It's a really good board, other than the fact that happened. It's got an accelerometer on there. It connects from the board using I2C, so it doesn't connect using the GPIO pins. So all those GPIO pins are kind of available for you to use for other things. But it's got all these nice headers, and it kind of offloads the complexity of setting the pulse width modulation and so on for the motors. So I was hoping to do a show on this and using this in a little project, but that'll have to wait while I get another one. So just thought I would tell you about that. Okay, so the little spinny logo tells me it's at this point in the video where YouTube will recommend over here another video for you to watch from the over 400 and nearly 50 videos that I've published on the channel so far. So definitely check one of them out. It's handpicked one just for you. And at this point in the video, I'll say thank you so much for watching, and I shall see you next time. Bye for now. And I'll hit the stream marker button there, and I will have a look and see what people have been talking about. So Martin just asked a question there about that carry board. We'll have a look at that in more detail in a second. So let me see what people have been talking about on here. So Laurie was saying, look, Python, MicroPython, my favourite language to program in. Yeah, once you start programming in it, why would you use any other language? It's just great. And Laurie was saying, has anybody considered about the Arduino and their changes to the terms and conditions on the website? So when I saw that Adafruit had kind of raised the flag saying, Arduino have just made some major changes to the terms and conditions, and they look pretty horrific from a consumer perspective. Like any code that you upload, they could essentially just own that code. Even if you decide later on to delete your account, they'll keep your account up there. and they can monetize that code that you've created and, you know, sell it to other people. And it's like, but if you created that code and you've chosen like a GPL, are they going to respect that? There's loads of questions like that. Arduino have since clarified their position on that, so I'm really pleased that Adafruit raised this and that Arduino have come back and said we'd like to clarify our position on this, and it does look like they've clarified some of the points there specifically. So it's only when you're uploading to the Arduino cloud, I understand, and it's just to do with if they want to host your code on their platform, they need to be able to share that with other people. That's the entire point of sharing your code. But it's kind of clumsy, the language I think that's been used in there, so they've clarified that a little bit. So my take on that is we'll judge them by their actions. And if they do really bad things, then you know, really bad things will happen. Hey Roland, how's it going? If you like C++ and Python, you can of course like both of them, of course. I just wanted to show that there's a direction of travel of people, more people using Micropython. So yeah, Dale says that supposedly it only applies to cloud services. It doesn't sound good, does it, though? So Dale's saying that, yeah, that's what I understand too, but I was thinking about using their cloud services, now not so sure. One of the things I think all companies struggle with is when they have some kind of AI service. So Arduino do have their IoT cloud. Let me just bring up a browser that's got that in. So I have got a, I go to app.arduino.cc. Wait for this to load up. So I've got quite a few things, as they call it. You can see there's two online. One of them is that little temperature sensor I was talking about behind me, just there. So if I find that one, which is online, which I think is this WeatherBot. If I go into the WeatherBot one, I can see that, you know, all the data that's come from that for 15 days. And if I go to the actual code of this, if I go to Sketches, I think it is, and I find that WeatherBot code. So where's the WeatherBot code? I'll just grab any code actually. Let me just grab this code here. So I'm in the web version of their IDE. They've got this little button here which is their AI assistant, and it's been really tuned to help you with code. So if on here, for example, I had like a typo that says L setup, and I try and compile this code and there's a problem, it'll pop up over here saying like how to fix this. So again, we do have to wait like an eternity for it to compile because it is C code, but it'll detect that there's a problem here, and on the left hand side it'll tell me how to fix it. And they've tuned their AI to work perfectly with their libraries, their boards, and common issues that occur. So that's one of the things that's really useful as a programmer. But they've had to train that model, and where have they trained it from? Where's the code come from for that? It's probably code that you've shared and you've allowed them to as part of the terms and conditions. So yeah, that's one of the things that's. Let's see if it's got the fix on there. So if I say fix my code, it'll have a look through and it'll tell me where the issue is. So there you go, typo in the logic, and so it should be in void setup. There you go. So fix was else setup, and you can basically just say, yep, I accept that, I'm happy with that. So apply that and it'll correct that. So there we go. Nice and easy to do. So that's part of their offering now. So let's see what else people are talking about. So Gojirantron said, hey, I'm here for once on time. Good. Back to the familiar music. My kids are bopping to that music in the intro. Me too. Let's see what everybody else is talking about. Yeah, the easiest to learn and to use. I think that's why a lot of these AI things are written in Python, because, you know, if you think AI, you would want it to be as fast as possible. Why is it not written in like Rust or C++? I understand that Cloudflare issue that tripped up ChatGPT and X this week, that was to do with a Rust code that wasn't tested properly. There's a file that was twice as big as they expected. Been away for ages. Still using Python and C++ on the Arduino Q. Yep, there's a real mixture of both of those, isn't there? God, for Gemini 3. So my audio apparently is a bit low. I'm not sure why that is. It looks to be the same level. Maybe the microphone was... Is it still low now, or is it okay now? I can see when I talk, it's peaking at the correct point. If I show you on this little view here, I have this little meter that's just on screen here. So when I'm talking, I can see where that should be. But yeah, I'm not sure why YouTube have made that a bit lower, perhaps. So Python and MicroPython wasn't easy. I've not been able to get 20-year-old hardware working. There we go. Tong, 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 tong. What is that? Ah, my phone was turned down. So DQ Soft, hi, I'm a Brazilian spending a couple of months in the Netherlands. Awesome, awesome. Hey Martin, how's it going? Yes, Python Excel. I was learning how to do k-means clustering in Python. That's really, really awesome. Very impressed with what you can do on there. Let's grab Excel and have a look at that. I think it's available in all the latest versions of Excel. So if you've got like Excel for the web, or you've got the latest desktop version of Excel. So if I go over here, I'm an absolute Excel nut. I love Excel. Why is that not showing my screen? There we go. So if I go in here, I type in equals pi. It should jump into the Python. There we go, Python. So you can say, you know, a equals 1, print hello world, whatever. I think there's even like a little window that can open at the other side. So if I now just come out of that. Ugh, that was terrible. You get the idea. You can write Python code in Excel now. It's intended for things like data frames, so you can do, you know, really complex kind of calculations and stuff in using Python's libraries, matplotlib and stuff like that. Pandas, absolutely. It's pretty cool. So you can add functions written in C or assembly to MicroPython 2. You get the speed up when you need it. So in fact, one of the things that's quite cool on the Arduino lab for MicroPython is when you add a package, you can actually opt to have that package. Oops, let me just grab the right thing there. Sorry, let me just find that again. Add package. Bring that down here. So one of the advanced options is to convert these to the MPy format. MPy format is like a compiled version. So Python and MicroPython convert to bytecode behind the scenes. So the interpreter has to have a step where it converts the text you've typed in into bytecode, and then bytecode is what gets executed on the Python virtual machine. So if you've got the bytecode already converted, it's one less thing that it needs to do, so it does speed it up. Using their MicroPython package installer, it automatically converts them to these MPys, so that's pretty cool. It just means it's that much faster to execute. But there are actually some, I was meaning to do a show about this. There's some really fast things you can do. So they call the thing that emits the code in Python the code emitter. I think there's 2 different things that you can do that will emit code even faster, but they've got very specific use cases, but it's like almost the same speed as C++. So I'll definitely look at doing a show on those. Yeah, so you can add functions written in C, C++ to MicroPython 2 to get the speed where you need, but keep the convenience for the rest of your code. Absolutely. I think Arduino Q is taking advantage of that. Actually, you can put semicolons at the end of Python lines if you want, they're just not required. Is that so? I'm going to try that and see if that anything happens. I know there's a language called Python where they've put the curly braces, and it's just Python with curly braces, so you don't have to have the indentation. But I don't see what the point of that is at all, to be honest. Yeah, they seem to accept that when I tried that example just then. So I feel if you get the semicolon in C when I've been working for Python in a while, yep. Me too. My Python shouts me that as well. You can use the auto in C++ to have the type inferred automatically. Is that so? The difference is mostly the fact that C++ a variable has a fixed type, whereas in Python they're an object in Python, aren't they? So you can change it, which is it's weird but also quite cool as well. So Hey Johnny, how's it going? So a robot arm video will be cool. Doesn't have to be complex arm even. So yes, we've created about 3 robot arms. I think we did a robot arm video. There's one on the floor just there actually, which is a robot arm from is it Waveshare who created that one? So I've got 2 of those robot arms. In fact, you can just see one just there. That's a professional robot arm. It has got a Raspberry Pi camera on it. So yeah, I could have one arm and you move one arm and the other one follows. That could be quite a cool project to do. So yeah, definitely make a note of that as a request from the audience. Let's make a note of that. So there we go. Made a note of that. They would like to see more of the Uno Q. We can definitely do more of that. I don't want to overload people with too many Uno Q videos, but they did do quite well on the channel actually. I guess because they're new and it's a new thing. One of the things I want to do with my Uno Q, wherever I put it, is to run ROS on there. So we did a ROS video last week, and yeah, I'd like to follow that up with using this for robotics. I'd also like to get something that uses these high-speed connectors on the back, but I've not seen anything out there yet that can do that. And they haven't released the 4 gig version of the board yet. So once that's out, that'll be quite cool to get that too. So Ford's busy doing chores at the moment, no worries. So Rory says, Uno Q2, love, but the blocks are not as intuitive as they should be. Having the SSH in to don't heat HTML block should be needed. Just following that message there. Not sure what you mean there. Is that the having the SSH in so you don't use the HTML block? Folder structure should be easy to manage too. Yeah, I think there's quite a lot of finesse that needs to happen in the Arduino app lab. There's definitely more room for improvement there. I know that they're looking at integrating that with the Arduino cloud as well. Yeah, there's quite a few robot arm videos. We did a simple robot arm. I did one where I used VM to control the robot arm as well. It's like almost like popsicle sticks. I think the YouTube changed how it displays account names in the chat some time ago. Is that so? Qualcomm buying Arduino was really changing in terms of the license is another good reason to switch. I did wonder if somebody would bring that up, but yeah, really the reason, if you look at the data, people have been switching from Micropython for quite some time. I remember back in the day when I had, I think the ESP8266 chips and ESP32s, before the Pico came out, I was flashing, and it was really janky. You had to get like an Arduino and connect the pins up to get it on these really small boards to flash that with Micropython. But once you've got it on there, it's so easy, and the web REPL, so you can connect to it to the IP address and run Python from there. Really, really cool. So Laurie says, yeah, hey, I've always purchased some boards from Arduino, even though the cheaper clones were available. I wanted to support their open source approach. Not sure now they are Qualcomm. I thought the same thing, Laurie. I thought now that they are like a proper commercial company and not an open source kind of foundation, that changes things. So should you be paying, over the odds prices for these boards, you're basically just giving them more money for not a lot really. Whereas you can buy the clone boards. I think I had one of those. So for example, I think I bought that Nano clone from somewhere online a while ago, and these are like dirt cheap compared to the official one. They do use better quality parts in the official ones, but when it just comes down to it, sometimes you just want the cheapest board to do the trick while you're prototyping. So yeah, I thought the same thing too. Yes. So CorePoint says, it seems like Qualcomm haven't lost any time with starting their corporate shenanigans, and I don't know what it's all about. I'm chronically annoyed with the world where it is. You've just got to let that go, I think. Yep. So Jeff says, not having to compile when you're troubleshooting your code is a huge time saver. Popping up a print line in Python and rerunning code to see where it's failing, it makes a big difference. Yeah, so much So much coolness. Yeah, Martin's loving the Nano 33 IoT for the win. I've not tried this properly yet. I think I need to give this a go. One of the other cool things, I think it's got with the... I'm thinking of something else. Yeah, I was just wondering, what's the benefit of this board over like an ESP32? About a similar kind of price, if I remember. What motor controller chips are on the Nano motor controller board? A good question. So you can see that there's actually 4 of them at the very top of the board there. Let me put it on the overhead and see if it's easier for that to be read actually. Oops. So that we can see what those are. Turn it around, maybe we can see them a bit easier. MPS 2046. Don't know if that tells you anything about it. But yeah, they're actually controlled. The motors are actually controlled over I2C. You can see that that chip that's got that hole in it. That's the voltage regulator apparently. So yeah, not sure what happened there. Really disappointed with that because it's a really nice board. I was hoping to build some robots with this. It's got the accelerometer on there with a magnetometer, which is pretty cool, and that worked perfectly. I even wrote a Micropython library for this, so it could work with Micropython and an Arduino ESP32. I've shared that code with Arduino, and they were like, yeah, we'll send this to the community. It's really cool. Thank you for that. So what voltages can the board handle for the motors? I believe it can handle quite a bit. On the back of the box it does actually say what the spec is when that gets into focus. So motor drivers, there you go, 1 amp, 12 volts. So pretty hefty. Max battery charging, so it can even charge up the battery. So I had an XT30 connector battery, like a drone battery, connected up to this, and it charged it up fine. And then I went to switch it off like that with a little on-off switch, and that's where it went poof, and the magic smoke came out, and I cried because I wanted one of these for so long. Here I am, just at the end of the show. No problem. Arduino IDE take a long time to compile code for ESP32. Right, it really does, doesn't it? I don't understand why that is so long. I think the main reason for switching for anything else is the new license. That means all your code now belongs to Qualcomm. They have since clarified that, and I don't think it quite means that the way that we originally thought. So if I go to Arduino CC, they have got a blog about that somewhere. Let's see if we can find that. It was on... I'm just looking on the Arduino blog. Let's see if we can find that. Jump back and go to blog. Directly blog. There we go. There we go, that one there. Terms of service, privacy and policy update, setting the record straight. Ooh, bit of handbag on there. So we've heard some questions and concerns following our recent TOCs and privacy updates. We're thankful for our community care enough to engage with us, and we believe transparency and open dialogue are foundational to Arduino. Let us be clear. Let us be absolutely clear. We have been open source long before it was fashionable. There's a bit of a tone here. Whoever wrote this seems a bit angry. We are not going to change now. The Qualcomm apposition doesn't modify how user data is handled or how we apply our open source principles. Well, if that's the case, why change the terms and conditions then? We periodically update our legal documents to reflect new features, evolving regulations and best practices. And that's where I think people have got a right to be a bit cynical about that. Why change them? Why make it more tipping in the favour of Qualcomm rather than what it was before? So open source and reverse engineering, this is one of the things that Adafruit have called out. So the terms and conditions specifically say you're not allowed to reverse engineer. And it says restrictions on reverse engineering apply specifically to our software as a service cloud applications. Anything that was open stays open. Ownership of your creations. The TNCs clarify the content you choose to publish on Arduino platform remains yours and can be used to enable features you've requested, such as cloud services and collaboration tools. That's fair enough. I know sometimes they have to include language that sounds quite legal. If you're sharing something, I was thinking the same thing with Kev's Robots. I'm going to have a feature soon where you can publish your projects, and I would have to have a similar kind of clause that says, if you're putting this onto my platform, I have the right to publish that because that's what you're wanting me to do on your behalf. But that can sound like I'm saying I own it when I don't own it. I'm just providing a platform. Now, there was something about miners' data and privacy. So our privacy disclosures have been strengthened, including enhanced protections for miners' data. We've updated our data retention policies and age limits to provide age-appropriate services. We limit data retention for inactive users by automatically deactivating their accounts within 24 months of inactivity, in which case usernames will be preserved, because people are saying that if you delete your account, your name would be preserved without your authority. In the Arduino forums to address the explicit request from the forum community to maintain attribution for user-generated content, whereas user request accounts deletion, the username would be promptly removed and related posts will become anonymous. So they really have kind of answered the questions that people were concerned about there. But yeah, this we are Arduino, we are open, we are not going anywhere. It sounds like anonymous. So yeah, just comes across as a bit angry to me, that as a response, as a bit of feedback, Arduino team. Yeah, dial it back a bit, I think. So yeah, I think that answers the question there. Main reason for switching is the new license. It scares people, stuff like this. When people are making an investment in a board, they want to know, can they trust what you do? And if you do things that look like you're beginning to be more untrustworthy, then that does frighten people. Friends don't let friends use Excel for data analysis. Excel can be quite cool. I've added a new feature to Kev's Robots, by the way, where you can actually see the stats. If I go to kevsrobots.com/stats, talking about data analysis, I used DuckDB behind the scenes to pull all these stats. So you can look on here and see how many visitors did we have last month. So we had 17,000 unique people, 63,000 visits last month, 85 searches, and 1,235 returning users. So you can see which days were kind of popular. I bet that's when the Arduino was released. You can see the kind of breakdown by device: desktop, mobile, tablet. You can just hover over to get the numbers. Visitors by country, so the USA, woohoo! Very, very popular with Kev's Robots, as well as all these other countries. And then you can see what's trending. I did have to adjust the algorithm I use to say what's trending, because if you typed in the same word and searched for it multiple times, it would bump into the top, and obviously that's not right. So whoever's searching for Pikachu, that's now been fixed. And this does get updated every hour, so it is quite live. You can see top searches this week: Python, Bluetooth, Pico, AI, Micropython. This just gives me an insight into what people are searching for. Is there any more content I should be creating around that? So ROS, maybe we need to do a bit more ROS content. And then you can see what the most popular pages are. So Pico projects, other than the home page, which I would expect is that highest page that people jump to. So you can click on that and you can jump into that page there as well. If you click on any of the searches, it'll also take you to that search page as well. So that particular one that somebody searched for, Pico Tama, returned no results. There's also this little thing that shows you like how popular this page has been. So when people have been searching over the past month. So October, we've only got data for October because that's when I published this little widget in the first place. And you can see how many times that page has been viewed as well. So all the stats are now on kevsrobots.com. Talking about friends not letting friends use Excel for data analysis. Yeah, there's always Jupyter Labs, that's true. Love Python, one ring to rule them all. Greetings from Bulgaria, awesome. Danny's here. So Danny says, hello, I've been having quite a bit of an adventure with Bamboo Labs Cyberbrick this weekend, printing lots of stuff and assembling, awesome. I'm still loving my Core 1. I'm thinking about printing out all the bits for the Core 1 Plus and getting the little plus symbol sticker on mine as well. So Copart says, revolume. Normally I'm local at 44 to 48 here. Today it's at 60. Move your mic closer. it's still on the quiet side. Something's different other than usual. I'm not sure what is different. The setup stays the same, the mic stays the same, so something has changed, I agree, but it might just be how perhaps my YouTube are processing it, perhaps. Anyway, Micropython, I can take some core code to many different boards. I love all things in the REPL, absolutely. Curious how your Cyberbrick project turns out. Caught my eye recently. Python now supports threading. Yeah, they've done threading for quite a while. I did a video on using multiple threads on Micropython probably about a year or two back. So you can search that one up on kevsrobots.com as well, or YouTube. If you want to find that particular video, you can do threads on Micropython. Not sure if it's mentioned, but ULab on Micropython is awesome. It's derived from NumPy, so fast vectorized math stuff. Cool. This people as well, let's see more robots. Absolutely. I've got my eye on a few robot projects, and I was hoping that this would be the core of one of my next projects, but yeah, that's dead, so that's not happening. So, bad autocorrect. Really wanted the camera module as having to add a USB hub for power and USB cam a bit clumsy. Yeah. Main fun with Cyberbricks are many 3D printable models around the ecosystem. I was tinkering with Micropython ESP8286s too. Yes, it's just so much better when you can use Python on a tiny little board. And these boards have like even less memory than like a Pico, the original one. And yeah, better go now. Thanks for another good stream, Kevin. Hope all of your American viewers are having a very happy Thanksgiving. See you here next week. Absolutely, yeah. Enjoy your Thanksgiving, everyone. And I shall see you all next time. Thanks for watching. Bye for now.